On the preceding slide, we showed that the Gibbs energy for the reactive mixture, G-mix, can be expressed as the sum of terms that involve the standard reaction Gibbs energy change as well as the Gibbs energy change due to mixing. We now want to use a similar approach to obtain an expression for delta Rg, the change in the Gibbs energy of the mixture as a result of the chemical reaction. Such an expression will allow us, among other things, to decide on the basis of the actual composition of the reactive mixture whether a given reaction occurs spontaneously or not. We consider the case of a general reaction between A moles of A and B moles of B to form C moles of C and D moles of D. We showed earlier that for such a reaction, the reaction Gibbs energy change delta Rg is equal to delta G divided by delta N and also equal to C times mu C plus D times mu D minus A times mu A minus B times mu B, where each chemical potential can be expressed as the standard chemical potential plus RT times the natural log of the species activity. This allows us to obtain an expression for delta Rg in terms of the standard chemical potentials for A, B, C, and D, the stoichiometric coefficient A, B, C, and D, and the activities for species A, B, C, and D. We group the various standard chemical potentials together and do the same for the natural log terms. We then recognize that the first four terms constitute the standard reaction Gibbs energy change delta Rg standard. In this equation, we have also used the relationship x times natural log of y equal to natural log of y to the power x. We start reorganizing the natural log terms using natural log of u plus natural log of v equals natural log of the product uv. Finally, we use the relationship natural log of u minus natural log of v equals natural log of u divided by v, which allows us to express delta Rg as delta Rg standard plus RT times the natural logarithm of a ratio of the activities of products divided by the activities of reactants, where each activity is raised to the power equal to the relevant stoichiometric coefficient. This last term is what we call the reaction quotient, Q. Note that delta Rg is equal to delta Rg standard when reactants and products are present in standard amount, which means 1 molar concentration for solutes and 1 bar for gases. This equation is very important as it allows you to determine at any stage of a reaction whether the reaction should proceed spontaneously or not. Some examples of its application will be examined on slides 11 and 12. This equation is also very important because it demonstrates that to fully judge the spontaneity of a chemical reaction, we need to know the value of delta Rg standard as well as the values of the activities, that is the concentrations or partial pressures, for all species involved in the reaction. That is, we need to know the composition of the reaction mixture. So when is the value of delta Rg standard sufficient for the determination of spontaneity? The only time the spontaneity of a chemical reaction can be judged without the specific calculation of Q is when reactants and products are present in standard concentration or at standard pressure. Indeed, in this case, all activities will be unity, Q will have a value of 1, and the natural log of Q will be 0. Before we proceed further, it would be worthwhile to make sure we know how to write Q for any reaction. On the preceding slide, we wrote the very important relationship between delta Rg standard, and the reaction quotient Q. We defined the relationship between reaction quotient and activities for a reaction between A and B to form C and D. On this slide, we practice writing reaction quotients. First, we need to recall the definition for activities of species in different phases. For a solute in an ideal dilute solution, we equate the activity of J with the ratio of the molarity of J to the standard concentration, 1 molar, the standard molarity. For a perfect or ideal gas in a mixture, we equate the activity of J with the ratio of the partial pressure of J to the standard pressure P standard. For a pure solid or liquid, the activity of J will be equal to 1. These definitions ensure that the activities are unitless and that the chemical potential of a species is equal to the standard chemical potential of that species when the species is present in standard concentration for a solute, or at the standard pressure for a gas, or pure for a pure liquid or solid. Our first example considers the simple isomerization reaction of glucose 6-phosphate to fructose 6-phosphate in aqueous solution, which we studied earlier. We write Q equal to the ratio of activity of the product, F6P, divided by activity of the reactant, G6P. For solutes in solution, assuming they follow the ideal dilute solution behavior for now, we replace activities by molarity divided by standard molarity, or 1 molar, to get Q equal ratio of molarity of F6P divided by molarity of G6P. No exponents are used in this reaction quotient since all stoichiometric coefficients are unity. Second, we examine the reaction between hemoglobin, Hb, and oxygen gas to form the hemoglobin complex HbO2 4 times, which contains 4 moles of oxygen per mole of hemoglobin. While this reaction occurs in solution, it requires the bubbling of oxygen gas. So we write Q equal activity of the hemoglobin complex divided by the product of the activity of the hemoglobin by the activity of oxygen raised to the 4th power, since there are 4 moles of oxygen in the reaction equation. For solutes in an ideal dilute solution, the activity is the ratio of the molarity by the standard molarity, 1 molar. For gases, the activity is the partial pressure of the gas divided by the standard pressure, or 1 bar. So we write Q as the ratio of the molarity of HbO2 4 times divided by C standard over the molarity of Hb divided by C standard, and by partial pressure of oxygen divided by standard pressure raised to the power 4. This equation can be simplified somewhat by cancelling out the standard molarities.